Unlike the ground motion excitation which we discussed previously, earthquake is usually expressed as ground acceleration in small time interval. The force imposed to the structure due to earthquake excitation can thus be expressed based on the Newton's second law of motion, while the term acceleration is replaced with ground acceleration. Recalling the equilibrium equation we use when we are discussing about the ground motion excitation. From that equation, we subtract the external force due to earthquake from both sides. Then, let's rearrange the equation based on the types of dynamic responses, namely acceleration, velocity, and displacement. We can introduce a new set of terms representing the responses associated with the relative motion. From here, we may further simplify the equilibrium equation. When focusing on the undamped SDOF system, we may substitute the external force function into the Duhamel's integral we produced previously. For damped system, let's try to produce its Duhamel's integral. Under this situation, the displacement response should include the effect of damping. Then, we make the initial displacement 0 and simplify the expression. Finally, we can proceed with constructing the integral. For further detail, you may refer to our previous video on impact load for SDOF system. At this point, we just substitute the external force function into the equation. From here, we know the dynamic response of a structure to earthquake excitation is depending on the magnitude of acceleration itself, damping, and natural period of the system. When designing a structure under earthquake, the engineer is interested to determine the maximum response. The displacement spectra can be calculated using the expression we have derived earlier on. The velocity spectra would be the product of the frequency of the damped system and displacement spectra. Where the damping ratio is less than 20%, frequency of the damped system is approximately the natural frequency of the system itself. Similarly, acceleration spectra may be derived from the product of system natural frequency and velocity spectra. Response spectra are also created based on certain seismic events. These spectra are used to determine the design values for displacement, velocity, and acceleration under the same event. To use the spectra, the system is often regarded as elastic, and the input required is solely its natural period. After knowing the spectral displacement of a system, we may proceed with the calculation of base shear by implementing Hooke's law. We may further transform the base shear equation and express it in terms of acceleration spectra. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.